Welcome back. In this video, we're going to prove another trig identity. What we're going to start with is cotangent phi plus cosecant phi equals sine of phi divided by 1 minus cosine phi. So when we go to work through these proofs, I encourage you to create a barrier wall, create that invisible wall. No, you're not going to ever cross it. So we can work on both sides, but we just never want to move a term. So an illegal move would say, if I was like, oh, I'm going to say minus cosecant phi and cancel. Completely illegal. We never want to do that. So we generally pick the more difficult looking side and start there. They both look equally funky maybe to you, but I would maybe pick cotangent and cosecant because right now I don't like those. I prefer things in terms of sine and cosine. So that's going to be my first step, to rewrite both of these as sine and cosine. So cotangent is cosine phi over sine of phi, and cosecant is reciprocal to sine. So there's my first step, rewriting everything as sine and cosine. Now it should look pretty easy to us to say, hey, let's try and add these two fractions. And if I do that, I have now cosine phi plus 1 over sine of phi. Well, they do start to look more similar, but they are not exactly the same. What should I do? This is where we pull in a strategy of multiplying by 1. And you might say, well, Miss Stein, there's no common denominator to get over here on the left. How am I going to choose my 1? And we do it by using conjugates. So this is especially helpful. Here I have cosine plus 1, cosine phi plus 1, and the conjugate of that is cosine phi minus 1. So if I put cosine phi minus 1 over itself, then what I have here in the light blue, that's just equal to 1, and it's okay to multiply by 1. So I use this strategy. I use it a lot when I have a radical, but also if I have two terms, and we'll see why. This is going to give me cosine squared phi minus 1 over sine of phi times cosine phi minus 1. So doing that and looking at what we have, I now see I've got something very similar here in the numerator. I've got cosine phi minus 1. Now, is that the same as 1 minus cosine phi? You should all answer no, because subtraction is not commutative, but it's starting to look more similar. All right, what should I try next? What is this numerator equal to? And most of you are probably saying or thinking, or we should be, that this looks like a Pythagorean identity. Is it specifically a Pythagorean identity? What do we know our Pythagorean identity to be? We know that sine squared x plus cosine squared x equals 1. So in order to make this in red look like my numerator, I would have to say cosine squared x equals 1 minus sine squared x, or rather cosine squared x minus 1 equals negative sine squared x. So what is my numerator equal to? My numerator is equal to negative sine squared x. So I have negative sine squared, and I'll use my variable in this problem, phi, over sine of phi times cosine of phi minus 1. All right, let's look where we're going. I've got a sine only in the numerator, so we want, and I'm going to actually bring that all the way down, we've got sine phi over 1 minus cosine phi. Can I simplify anything on the left here? So on the left, I can factor out a GCF, and I can cancel that because it would be 1. So I have negative sine of phi over cosine phi minus 1. Are these exactly the same? Not quite. We have a negative 1 in the numerator. What would happen if I put that negative 1 in the denominator? Or rather, you could think about it this way, multiplying by 1, which would be negative 1 over negative 1. That gives us the sine of phi over negative cosine phi plus 1. And are these the same? Rearranging the terms in the denominator, that would be 1 minus cosine phi. At this point, we are done. We'll end our problem with a therefore. I hope that helps you understand proofs a little bit more. I've got quite a few more proof examples for us to do together. Send me emails if you have any questions. And really remember, the best way to do these is to put your pencil on the paper and work through them on your own. All right, good luck out there in the real world.